Your organ starts out as a set of detailed computer drawings. Computer drafting, or CAD drawing, allows us to plan the exact position of every pipe in the organ. These drawings will guide our computer-controlled cutting system as it mills out the complex array of holes and channels that will be needed. The process of preparing these drawings takes several weeks. The wind chests form a sort of table on which the pipes sit. The top of the table is called the toe board, and each pipe sits in a carefully dimensioned and beveled hole. Under the toe boards, an array of electromechanical valves will be placed, one for each pipe. For tonal reasons, most of the pipes are offset from their valves by a channel in the toe board. These channels serve to reduce the sudden impact of the air at the foot of the pipe by creating a baffle between the valve and the pipe. Most of the mechanical portions of the organ are built of a special Baltic birch plywood, so called because it is imported from the Baltic region of Europe. This material is dimensionally stable and voidless, meaning that there are no holes or gaps hidden inside the material. In a Reynolds pipe organ, most of the toe boards are 2.5 inches thick. This is to allow a solid foundation for the pipes and enough thickness for the channels and for the hardware that attaches the valves. We purchase Baltic birch wood in 3/4 inch thickness so the sheets are manageable. The first step in the wood shop is to laminate the sheets that will become the bottoms of the toe boards. To do this, we use a vacuum laminating machine that was designed and built in our shop by David Reynolds a number of years ago. In a carefully choreographed process, the sheets are staged beside the vacuum table. After the dust is blown off, a generous amount of wood glue is applied to the entire face of one of the sheets. Here we see Corey Klein applying the glue with a paint roller. The amount of glue applied is critical. Too much glue and the pressure will make it foam out of the joint. Too little, and there will be gaps where air could bleed between notes. Corey has to work quickly and confidently. He doesn't want the moisture from the glue to begin to warp the wood. Once the glue has been applied, the top sheet is carefully placed. Since the top sheet is now floating on a layer of glue, David throws a couple of staples in the corners of each piece to maintain the alignment. Rubber sheets are placed on top of the sandwich to provide cushioning. Then the sandwich of 2 large sheets of plywood with glue between them is quickly moved onto the laminating table, and its position is carefully adjusted. The special reinforced plastic sheet covers everything and is securely clamped all along the 4 sides. This sheet must maintain a vacuum underneath without leaking. David starts the compressor, which draws a vacuum under the plastic sheet, squeezing the plywood sandwich together. The clamping force caused by the weight of the atmosphere, not by the plastic sheet, is an incredible 22,600 pounds of force. After an hour under this intense pressure, glue has been forced into the fibers of the wood, and the two sheets have bonded. The joint between them is actually stronger than the wood itself. This material is now ready to be machined into toe boards for the new organ. The drawings that were so carefully prepared have been translated into a machine language called G-code that contains the commands for the computer-controlled cutting system. David has planned which pieces can be cut from each double-thick sheet, and the computer has planned the path of the cutting head. The first toe boards will be for the chest that will hold the visible pipes on the left side of the chancel, which will play from the center or grate keyboard. A sheet is placed on the table of the CNC router. The gantry and cutting head are aligned, and the height of the bit is zeroed against the material. Once this is done, Corey presses the start button and the machine begins to cut. A very complex cut like this sheet of channel boards may take as much as an entire day to cut. During that time, Corey watches it, looking for any chips that might jam the cutter. The cutting must be done in several passes, since trying to remove too much material all at once would ruin the bit and damage the machine. Often, while the CNC machine is cutting, sheets can be laminated since the two machines are adjacent to each other. When a note is played on the organ, the channels you see will be pressurized. If even a tiny amount of this pressurized air is able to seep into an adjacent channel, the pipe on that channel may play faintly, making the note sound out of tune. To prevent this, we flood the channels with a special type of glue that cures into a rubbery coating when it dries. Here you can see Corey applying this treatment. The channels are filled with glue, which is allowed to soak into the wood grain for several minutes. Then he uses a vacuum pump to remove the excess, which is caught in a bottle to be reused. Once the channels are dry, the toe board is ready to receive its top. This top has the beveled toe holes in which the pipes will sit. In our drawing, the top is another layer, perfectly aligned with the channel boards we have just cut and sized. The new pipes for the organ were ordered several months ago. The flue pipes are produced in a pipe shop in the Czech Republic. We selected the Rieger Company as our pipe supplier because of their superior craftsmanship and the consistently high quality of the pipes they have supplied to us for nearly 30 years. The new pipes start out as sheets of a special metal called spotted metal. The name comes from the texture of the material, which is 52% tin, 47% lead, with trace amounts of other metals such as antimony. This metal is chosen for its stability and for the warm, distinguished sound it imparts to the pipes. Earlier this year, our pipe makers rejected a whole shipment of metal because it did not meet their standards. Less conscientious craftsmen and women might have used this metal to make your pipes. Rieger did not because the metal hadn't fully cured and was not ready to be formed into finished pipework. When we ordered your pipes, we specified many aspects of their construction, including their scale, the thickness of the metal, the wind pressure, and how the pipes would be tuned. The pipe shop received very specific instructions for each set of pipes we ordered. Once the metal is ready, the master pipe makers set to work. Using special patterns and very sharp tools, they cut the metal out for each body of the pipe. For this organ, the pipe maker will supply 996 new organ pipes, roughly half the total number of pipes in the organ. After the metal is cut, the body of each pipe is given its round shape on a steel mandrel. As you can see here, this process, called rounding, is actually done with a hardwood tool called a beater. The metal is literally beaten into round. This process not only shapes the pipe, but also relaxes the metal. A fine solder seam is then run up the back of the pipe body, and it is ready to be joined to the foot. When the bodies are done, the feet are made by a similar process. The lips are cut and formed, and a piece of metal is carefully placed at the point where the foot and the body join. This piece is called the languid. Each step requires careful and very precise soldering. If the metal is too cool, the pieces won't join. Too hot, and they become a puddle of molten metal. The last step is soldering the body, the foot, and the languid together. Before this is done, a liquid that looks like paint is applied all around the parts to be soldered. This is called pipe size, and its purpose is to prevent the solder from sticking where it shouldn't, and to protect the adjacent metal from the heat of the iron. We'll be talking a lot more about the pipes in the coming weeks and months.